Welcome back. This will be our final in-class kind of lecture. Obviously, we're all meeting up next Tuesday at 9:45 for our final demo day. I'll send a Canvas and Discord message today or tomorrow about the link to the slides and to the Qualtrics survey. But otherwise, just know to be here on Tuesday, your entire team, and I think we'll have more than enough time to get through all of that. I was joking a little bit, but this is a 15-plus week semester. Probably enough content for 20 in this course, so you're welcome if you want to learn more. There's other mechanisms by which we can learn more. Any of you who are continuing on for graduate school and need a topic, right? You're doing a creative component or a master's thesis. It's not like immediately obvious what that topic would be, but if this type of area is interesting to you, we can certainly find something. There's lots of fun, low-hanging fruit. You can look back to maybe the parts of the class you found the most interesting, or the parts that maybe are the most forward-looking, and see what would be a valid project for you, and we can go through that process. And that offer is open to anyone who has come here regularly this semester in class. It is open to all of you, and I'm happy to work with any of you. It's something that I enjoy doing. Otherwise, good luck. I know there's one more push on your project between now and Tuesday. Focus on functionality, focus on your rubric, focus on what you'll be able to show for that demo day, and I think you'll be happy with the end result. I would like to avoid, I know it can always happen, I would like to avoid where the demo day is, well, we tried, and that happens, I get that, but I think everyone has doable projects, and even if it's not exactly what you want, I think you can kind of find in the spirit of compromise something that kind of gets you a good chunk of the way there. So where we left off on Tuesday is we were starting to look a little bit at that kind of assembly format, and one of the main takeaways I wanted you to have from that is that there are a couple features that do make this PTX virtual assembly a little different than what you would have learned in prior embedded or architecture courses, but really not all that different. And some of the features that are newer for that assembly language now at this point in the semester are no longer new to us, like the special functions that we have there. We now have a pretty good feel of both why those are necessary, basically to do lighting calculations if nothing else, and why there would be a valid reason to have them as kind of native instructions versus just software library calls in the underlying architecture. Otherwise though, if you combine those two kind of features, one is basic RISC style ISA, and then shading compatibility assembly instructions, that is essentially what your PTX virtual assembly ISA is going to look like. To the extent that even though we are not, I would say, yet at the level of experts with regards to, doing CUDA, we won't have a lab where we get to do it in this course. I think we can kind of squint at a reasonably advanced CUDA kernel and look at what happens at the resulting PTX assembly. We started that a little bit on Tuesday, but I didn't want to rush it, so we cut it off there on Tuesday. So this is a CUDA kernel that is attempting to do C equals A times B. Given widths of matrix A and matrix B, it's doing matrix-matrix multiplication. An algorithm ourselves that we know how to do. If I asked you to write that in C or Python or MATLAB, you'd have different implementations for those, but you would know and be able to do that. This is not that different from then just the vector sum, the vector addition one that we looked at to kind of kick things off with regards to CUDA, but it's now kind of a two-dimensional problem, right, as opposed to that one-dimensional problem. So going back to this kind of inherent question of, for a problem I want to solve, what is the right dimensionality of kind of the thread work that I'm allocating on the device? Always we know there is no right answer. There is no one correct answer. Part of the answer is oftentimes the work dimensionality follows the data dimensionality. If I have just a single dimensional arrays, it might make sense to have just single dimensional blocks for our threads. Here we have two-dimensional arrays for our matrices. It can make sense to have then two-dimensional layouts of threads in our block. The other aspect of the answer to that question goes back to that spreadsheet view that we kind of sort of played around with on Tuesday, which is my goal is to increase the occupancy of that device. Occupancy being defined as the number of blocks, and resulting warps of threads I can have executing in parallel on the device at any given point in time. With the caveat that occupancy does not equal performance, but beyond that, I think it's okay to say higher occupancy is a good thing. We're more likely to be taking good advantage of the compute resources we have available, primarily to allow us to hide that off-chip memory latency. I get more threads, I can fit more blocks on a streaming multiprocessor at a given point in time. That would mean we have a higher likelihood that when we get to a load instruction, and it's going to take 600 cycles for that warp to execute the load instruction because it's missing in the cache, I am more likely to have enough available additional separate warps doing other parts of that same kernel that allow me to keep things going. That my CUDA cores, my floating point units are staying full at a sufficiently high enough rate that I'm doing about as good as I can on a given device, which is all the computational resources I have are busy. They're all doing work. Well, if you have 10,000 of these CUDA cores and all 10,000 are constantly doing some useful computation, at least in terms of an implementation perspective, that's about as good as you can hope for. Algorithmically, there can be all sorts of separate cleverness that may be possible, but in terms of the underlying implementation, every computational resource being busy is what we hope for when we're trying to parallelize something on a device. And that applies to all sorts of heterogeneous and other types of computing devices, and it's certainly going to be true here. So looking at this matrix multiplication CUDA, I say, the data, if it's a matrix, is kind of, we think of it as a two-dimensional data, so it kind of makes sense, at least in this kind of baseline vanilla implementation, that we are going to have two-dimensional blocks. So here we have our block index.x and block index.y. That strongly implies that when we launch this grid of kernels, for this kernel, we have a two-dimensional layout of threads inside a block. It does not necessarily tell us the layout of blocks inside the grid, but that's something of a separate consideration, right? We are limited in terms of any synchronization we want to do in our kernel to only communicate and only synchronize amongst threads that are within the same block. So that dimensionality is the first and primary consideration here. We then have multiple blocks inside of a grid if we have either some very coarse-grained parallelism that we can take advantage of, or if we just want to make sure we have a mechanism to get lots of blocks spawned at the same kernel invocation time. So we have our two-dimensional block index, so that can give us our index of x and y. We would then take via the same kind of kernel index bookkeeping a way of considering what region of the matrix is this particular thread going to be responsible for. I don't want us to worry too much about this yet, but that's all that this code is doing. What is my beginning in matrix A? What is my step size in A? And what is my endpoint in A? Likewise for B. And then in terms of the underlying computation, there's kind of a two-step process that this code does. And I'm not saying when I show you this that this is the exact correct way to do it. There's many different ways. Probably the most analyzed block of code in all of history is matrix multiplication. So there are many such type of approaches. This approach takes the shared memory approach. We talked about architecturally how there is a relatively small amount of data cache. In addition to that data cache, which is a CPRE 381 style data cache, there's also this software managed memory. The term you may have heard in an embedded systems context is scratchpad memory. Here it's just referred to as shared memory. It's the exact same concept. It's just another block of usually SRAM memory that is like a cache, but whereas a traditional cache is hardware managed. All I mean by that is you have your tag field of your address, and it's checking the tag field and the valid bit and confirming whether it's a hit or a miss. It's all happening kind of independently of the load instruction itself. And hopefully some of that sounds familiar. Certainly you've been playing around with caches this semester. That is a traditional, we call it a hardware managed cache. A software managed cache is also a cache. It's a place where you can store data so it's closer to your computation and you should be able to access it more quickly. But it's software managed in the sense that I, as the programmer, have to manually decide what entries should be in that memory at any given point in time. So there's advantages and disadvantages. The advantage of a traditional cache is I don't have to think about it, by and large, as a programmer. It's just this memory that's there for me, and if I have good locality in my application, the cache will do a good job of keeping things I need in that small memory for me. In the software managed cache, I have to be aware of it. I have to actually put things in that software managed shared memory myself, that scratchpad memory. But the advantage there is if I really do know what my application needs are, I can presumably do even better than what a hardware managed cache can do. Because as the programmer, I'm hyper aware or can be hyper aware of what do I need to have available at any given point in time. And I can write my application so that I'm taking advantage of that in as appropriate as a manner as possible. So that's the first part of this two-phase solution for the matrix multiplication here, that for the chunk of work that this thread is going to be responsible for, and that's all that the for loop is kind of doing here. Maybe it looks a little ugly where it's doing both A and B in the for loop, but that's all it's doing here. So it's an A index and a B index type for loop here. We are declaring that for all the threads in this block, there's going to be a shared region of memory accessible to all those threads in the block. And then each thread is going to be responsible for copying a subset of the data for matrix A and B that would otherwise be in global memory, and it's going to copy that into the shared memory. You might say, well, that's going to be pretty slow. And it will be, right? We're going to be doing all just load instructions, maybe a little bit of arithmetic to generate the addresses here, but otherwise just a series of load instructions. And if we look at the resulting generated PTX assembly code for it here, yeah, you see some additions and multiplications to do that index offsetting that we have here. And you can see addition and multiplication going on here. And then the rest are just load and store instructions. Load from global memory, store into shared memory. Load from global memory, shared into stored memory. All of these threads are going to be doing effectively just loads and stores here at a given block in time. That is going to be slow. Those are presumably going to have some cache performance, but it's loading, but it's going to be slow because we have to wait for that global memory. For a matrix multiplication operation, that may be tolerable from a performance perspective. We may be okay with that, right? I'm going to load in order n squared of data, but I'm going to do order n cubed of computation with it, right? So we pay that n squared penalty, but we're doing n cubed computation, and it kind of gets amortized. It's not that big of a latency that we're facing there. Here, as we're doing this, as we grab each element, we're making sure that we have the entire matrices loaded at a given point in time before we start the computation. This is one of the primary mechanisms by which all of the threads in a block can then coordinate. It is implemented via like a barrier type instruction where every thread reaches this instruction, and there's some sort of atomic memory access in terms of how it's implemented under the hood. Again, the actual implementation details for that aren't that clear to me, but that's how we would traditionally implement such a thing. And every instruction in the thread, once one of them reaches that instruction, they all have to reach that instruction before it can proceed past it. That's a little bit hidden in just the name. It doesn't look like it's doing all that much with a barrier sync here, but that's what's happening. You can do that in most modern assembly languages for similar reasons as well. We've copied a block of memory in. We have some of our A sub s and B sub s implemented here, and then we can do that computation going on here. We have a simple for loop as well as a pragma saying this is a for loop. We write it as a for loop because that's, as a programmer, that's like the natural way to write it, but we actually don't care that it's a loop. Just unroll that loop. And if you've taken other courses that explore a little bit of software optimization, it's a very common type of software optimization. For our purposes, with some of the limitations of how we're executing our code as warps of threads at a time, we almost always want to unroll loops by a certain constant factor here. And we can just kind of give a hint that says, I don't actually remember why it's commented out. We can give a hint that says, unroll this. This is a for loop. That's a for loop that's written that way for programmer convenience. I actually want, for the block size, I want a whole separate set of those instructions doing multiplication of those two entries and then accumulation of those two entries. That is oftentimes going to be implemented as what's referred to as like a fused multiply add instruction here, and that's what eventually we should see. So we're doing some adds and multiplications to get our index into the array. We're doing loads and stores, grab from global memory, put into shared memory, and then there should be, because of how this is written here, a block size number of fused multiply add instructions, loads followed by fused multiply add instructions, load from AS, load from BS, do a multiply accumulate operation, and do this many number of them. Not in parallel, it's still kind of sequential, but without having to deal with all the for loop logic there. Basically, the for loop, when it's compiled down to assembly code, is getting removed entirely. block size is a constant from the compiler's perspective, we should have those patterns. Load, load, FMA, load, load, FMA, all the way down for whatever block size is for that application. And synchronize once that block is done. And there should be another sync threads down here, which there is. We still have our upper level for loop here, so there's a little bit of that RISC assembly style, check our values, and branch back to the beginning of that loop. Otherwise, that's kind of the end of that kernel's implementation. I think a valid takeaway from this is I think you do have developed the skills, not just through this semester, but through your curriculum here at Iowa State, to be able to look at that assembly and not be kind of thrown off by it. It is really ultimately nothing all that different with what's here. This example for matrix doesn't do any of the so-called special function units, but we also separately know now through this course why those units exist, why those assembly instructions would exist here. Otherwise, though, it looks just like 381 style assembly with a little bit of extra optimization thrown in. We can skip. Let's talk a little bit about memory management. That was inherent in all of these examples, and I mentioned it's not a difficult thing. Well, it's something that you have to get working and debug. All of these examples would be doing memory allocation here for these. This is a much more kind of C++ kind of way of checking that the actual allocation is done properly. But this is the very conventional way of doing memory allocation in CUDA, because it is a slightly separate beast. Now, that is slowly changing. When you have various devices now that have what's referred to as a unified address space or unified memory architecture, the design philosophy behind that is that you can treat memory allocation in your GPU's address space, the device's address space, as effectively just a special case of allocation on the entire system that you have. So you'll see some other examples that don't treat it as separate, but this is still the very conventional way that we do our memory allocation. We need separate functions for allocating on the CPU side and then allocating on the GPU side. Because they are two separate things, right? There's, at least physically, you have your regular DDR memory for your host side, all that you need to do your work there. You have allocation now for your device side, and we have a mechanism for both managing that and copying data and buffers around in your system. With the caveat that this is something that's changing at a pretty rapid pace here, this is still the conventional way to do your CUDA memory management and your allocation here, where instead of a traditional malloc call, you have CUDA malloc. And this is just a design decision. Instead of returning a pointer, you pass it a reference to a pointer, and so it overwrites the pointer. You just have to know that that's how it's done. Same, CUDA memset is very similar to memset. The pointer that you pass, it has to be the pointer that was a return function of a CUDA malloc call, but you then can set your memory or initialize it all to 0. You can also do your freeing functions here. And oftentimes, it's wrapped in some sort of helper function that takes care of some of the error checking and determining when things go wrong for you, so you can kind of eliminate some of the boilerplate code you may have in your example here. This is for the matrix multiplication example. Ignoring kind of the helper function on the periphery here, we're specifying, given how much memory for our host side matrices A and B, we are also then going to allocate the same number of bytes for the device side A, B, and then consequently C for that dimension as well. CUDA malloc, we pass it basically a pointer to a pointer because we're going to overwrite that pointer. It could have also returned a pointer, but instead we're overwriting a pointer, number of bytes we want. Same for B, same for C. We then have to do effectively a memcopy operation. It's extremely similar to a traditional memcopy, except now we have to be a bit more explicit in terms of what direction we're doing the copying. Right? Traditional memcopy, we don't think in those terms. Oftentimes we have to quickly look up which one is source and which one is destination, but once you've done that, we know it goes from source to destination in our memcopy. Here, we generally pass the device pointers first, then the host pointer, but then we separately specify via a little enumerated input here, what direction are we doing that copy in. So in this case, we do all the initial memory initialization for our matrices on the host. So we're going to want to copy those A and B matrices from the host to the device, and that's why that value is listed there. Once we've done all the kernel launching and done all the computation and have the correct result C back out, there is eventually going to be a memory copy somewhere in this code that's going to copy things back. Just take my word for it. Copy things back from the device side back to the host. So it's a little different. They could have implemented, I mean, there's no requirement it be done that way, that you always list host, then device pointer, and then you separately specify what direction things are being passed here. That's the mechanism that CUDA uses to do this memory allocation. So for this example given on this slide, we specify here's the number of bytes we're interested in. Here's a pointer to what would be an array of integers. We pass CUDA, we call CUDA malloc, where we pass a pointer to that pointer to overwrite that pointer. Instead of returning a pointer, we then call memset on that pointer to set it all to zeros. And then finally, once we've done whatever arithmetic we're doing on that, whatever kernel launch, we call CUDA free at the very end to then free that memory on the device. This example is good to go, or does it have a small typo or error in it? It has a mistake in it. What is the mistake, Andrew? You see it? It should be just CUDA memset, yes. So when I put that together, I thought that was a very clever idea, but that's fine. Oftentimes for these, I do think when it's time for you to go out in the world and write your first CUDA code, you're still very much better off starting with an existing working solution and modifying it versus starting entirely from a blank slate, open file, blank file for this kind of thing. You look at that and you say, I will never make that error. But if you start from blank slate, you will make that nature of error. And for better or for worse, at least just based on my own experience with CUDA and with OpenCL, when you have that kind of quote-unquote trivial error, it's actually very hard to track down. The compiler, because it's not a compiler error at all, right? The compiler will not say, oh, are you sure you didn't want to call CUDA memset here versus memset? It's just going to give a really opaque kind of crash because this is a pointer that is not valid from the perspective of the host operating system to be corresponding to any region of memory on the host operating system. But it is still a valid pointer. It's not a null pointer. It has some 64-bit value in that corresponds to some address, some location. So it's not going to be that easy to track down. Your code is going to crash in kind of opaque way. And a big chunk of modern, CUDA, OpenCL programming, as well as graphics programming, of course, is just dealing with the various buffers you have in your system. So, okay, this is a trivial error that you can catch just looking at the slide here, starting with an existing example that's close enough to what you are interested in doing and modifying, at least until you really get your feet under you, is probably still the right way to go with regards to this. So I think I mentioned this. This is the CUDA memcopy calls. Used for copying in both directions. It is generally a blocking call. It does not return until all of the bytes have been copied and all the CUDA kernels have been finished. This is mostly deprecated in the sense of that we do now have a unified memory model. You look at most OpenCL code, and they use the same function calls, OpenCL function calls for both host side allocation and device side allocation. But the CUDA approach still uses these CUDA malloc, CUDA memcopy kind of approaches here. When we do that copy, it's a little unique, but we do have to specify what direction we are doing that copy. And the example that I have here doesn't use this one, but this would be a valid thing to want to do as well. I have a buffer of memory on the device. I want to copy to another buffer of memory on the device. I would then do a CUDA memcopy device to device kind of copy here.
Do you give two device pointers?
Yeah, it'd be two device pointers for that. The example here is how we would do memory allocation here, but I think we got it. It's a matrix, 25 by 25, so you'd copy 25 by 25 times size of float. You'd first allocate, then you do a memcopy, do the multiplication, you copy the results back off. I think we got it. This is no different than basic malloc and dealing with matrices and keeping track of what the size of my memory needs to be. Of course, this is where NumPy and MATLAB make your life a lot easier, right? Where you don't really have to ever think about these issues. And given CUDA bindings for Python, you may in fact find your life a lot easier than doing it in C. But still, it's very much the case that all sorts of modern CUDA code is written in this fashion, where we are still manually doing our memory allocation. That is not a dated approach for dealing with CUDA. But I think we got it. I think we can handle this example, so I'm not going to spend too much time on it here. Now let's talk more about what we're doing when we're launching the kernels. We have the keywords. I think we know that we have what looks kind of like a function call, and in a sense it is. These are our arguments to the kernel launch. They tend to be pointers, although we saw some constants or values provided here as well. And they tend to be pointers because that is how we generally would parallelize our work, right? From an individual kernel, we write it from a thread's perspective. Each thread would then be receiving the same base addresses in memory, the same input pointers, and then each thread inside a block is going to then determine, or thread within the entire grid of threads here, what subset of that memory is mine. And it could be overlapping, but what subset of the overall work is mine, and it's going to use that same base address to then determine, given my own index, which thread am I inside the block, which block am I inside the grid, what is my section of work going to be. It tends to be the kind of thing that we can visualize for the 1D case, okay, usually pretty well, just use thread index.x. We can do it for the two-dimensional case, whether or not that's optimal or not, but we can kind of think our way through it for the kind of the two-dimensional case as well, .x, .y. Can start to think about it for a three-dimensional case, but where this gets tricky here is when we recognize that we have up to kind of 9 dimensions of thread layout available to us. With that restriction that there's just some resource limitations, right? We have certain IDs and registers that are a certain width in our implementation, and we're limited to this many threads per block. But within those limitations, we have potentially a 3-dimensional block dimension and up to a 3-dimensional grid dimension here. And so when we launch our kernel, our general launching command is going to look something like this, or this example that's given down here. Now, you have this dim3 type, which is just one small little addition to CUDA that's not itself native in C or C++. You don't have to use all 3 dimensions. So this example here is perfectly valid as well. The data type is referred to as dim3, but you can specify just 2 inputs and make it effectively what would be called a dim2. There just isn't a dim2 type. It's still a dim3 type. So for this example, we're specifying we have a block that's 25 by 25 threads. This example is arbitrary, but that's what we have here, 25 by 25 threads. And then we have a grid, which is 16 by 16 blocks. So we can do the math, whatever 16 times 16 times 25 times 25, total number of threads is what's getting launched in this singular kernel call here. If we just have a single dimension for any of those 2 parameters, block size or grid size, we don't need to use those types. So in this case, we could have, we want a grid of 32 blocks, and we list that first, and we want to have 512 threads total, and both of those would just be single dimensional. But again, although it goes back to kind of the big picture question of conceptually how do we parallelize our work, in terms of the code we're writing then as a sort of a separate issue, this becomes kind of the real challenge of writing CUDA code and writing effective CUDA code. Not just what is the right numbers for this, but how do we write code that takes advantage of the dimensionality of our thread layout is something that's worth doing at least once in your life and kind of working through the issues there. For me at least, I have to draw it out. And I'm limited to my inability to draw, multi-dimensional things beyond 3 dimensions. But you can kind of get to 4 without too much difficulty. Maybe have stacks of paper if you get to the 5th dimension. After that, I'm kind of out of luck. But for up to that many dimensions, you can still kind of draw it out. We have these built-in variables inside the kernel itself. So it's not listed as an input to the kernel, but each thread in the kernel has access to these built-in kind of constants that get assigned by the workload scheduler here, where they're given as input the grid dimension. This is the number of blocks inside our grid. We then have the block dimension, the number of threads inside that block. Those are constants for the kernel launch, across the entire kernel launch. Basically, whatever you specify here, the variable in your CUDA doesn't need to be called grid and block, but that's as good a name as anything, right? Whatever you specify here when you launch your kernel are going to be available to the kernel when you write that piece of code as constants, grid dim and block dim. Yeah.
Why is grid dim limited to 2 dimensions?
it's not a typo. That's an older artifact. So you can still think of it as X, Y, Z. I have a little trouble thinking about specifically for grid dimension, which is how we do that kind of maybe very coarse grained parallelism, why you would ever actually need more than one dimension for a grid layout. So while we'll go through this example, a lot of time the real work you're doing is for the block dimension and the block indexing here. So as I saw that's not a typo exactly. It's valid for when the slide was put together. It's also not that important either, but the same concept of how do I deal with all the dimensionality that I have here. So each kernel basically can treat these as constants. It's the same for every thread in the kernel. They all have the same 16 by 16 cross 16 or 25 cross 25 for my grid dimension, block dimension. That variable with built in would have a .x, .y, and .z for basically the x dimension of the grid, the y dimension of the grid, potentially the z dimension of the grid, and likewise for the block as well. So that's kind of provided that's constant for all threads in the kernel launch, because that's the size. That's like the width, height, and depth of my potentially three-dimensional layout here. And then for each thread separately, depending on where it is in the total invocation of all the threads that we have here, they're going to each have their own unique index. Block index and thread index. And as it kind of sounds, although it is kind of easy to get it mixed up because block index refers to my index within the grid. So block index is relative to grid dimension, and thread index is relative to block dimension here. If you draw it out, that makes sense. If you go back to that previous figure on like slide 12 or whatever it was in this slide deck, that is correct, but it's just you have to kind of keep track of what's happening there. Threads are within a block, blocks are within a grid. So consequently, inside a singular block, I have a thread index. Where am I in .x, .y, .z inside that individual block? And then I'm part of a block, which is part of a grid. So where is that block index .x, .y, potentially .z within my entire grid here? The dimensions are fixed when you do the launch. Each thread, or each block, and then consequently each thread inside the block are going to get their own separate values for that index. This is what allows us basically to partition up the work then. You're given a .xyz for your thread index inside the block, and now I have to determine for my particular problem, what does that mean for me? And a very common design pattern, and I've mentioned this a couple times already, is that we take those four kind of built-in variables, grid dim, block index, thread index, and the very first thing we do in our kernel, the very first line of code we write in our kernel is, can I figure out a unique singular index given these four values here, and given the dimensionality of my problem? We can try it in 9 dimensions, or we can work our way up to 9 dimensions, and either one is fine with me. This is an in-class exercise, so take a couple minutes and think about it before I just tell you, my approach to the problem. So let's just take a couple minutes. How would I compute a unique thread index for every thread, given block of .xyz, given grid of .xyz? How would I get a separate value for every single thread in my launch? If you start with one dimension and work your way to 2, once you get from 1 to 2, it's the same design pattern. But get from 1 to 2, and then we'll come back together in like 2 minutes here and see what that would mean for 2 to 3, 3 to 4, etc. I can attempt to draw it here as well, but we'll see how well that goes. Discuss, chat, say hello.
With arrays, just our two-dimensional array, you can arithmetic by doing like width, or what is it? It's height times something plus the width. The other way around.
Something like that.
Yeah.
So I think we would take unique block index.
take whatever it's y index
Times
y index times the width
yeah, plus the x index.
plus
Now
x
it's
index.
and you do the same thing for the threads inside.
So I've already given up trying to draw it. This is not my touch screen, and I don't have a mouse. Imagine I was capable of drawing it, and we could show. For one dimension, it's okay, right? For one dimension, if everything's one dimension, just that dot x kind of gets us at least within the block what we want. Discussion happening up here is exactly the kind of thing where you would have seen something like this before. Depending on when you took the class or who you took it with, in an undergraduate architecture class, this does come up because we have the same exact issue. We usually only explore it up to 2 dimensions, but it would be the same issue for 3, 4, 5, 6, 7, up to 9 dimensions as well. Which is if in my C code, I have something like int a of a certain dimension, certain size in an x and a y dimension here. And here, it's not as clear what's x, what's y, but we have a 2-dimensional layout of memory. We know that when that gets assembled back down, ultimately, we have a single-dimensional memory access, right? It's load instruction, load word, I don't remember how to do this, R1, with some offset of base address S1 or something like that, right? I think that's valid MIPS, right? Where somewhere in our code, we are doing basically that kind of dimensionality reduction operation, right? We are recognizing that what we want to have in our code is like C equals A of 5 of 9, right? I want to grab that, or I of j would be fine as well, right? I want to grab A of I of j in my code at some point. But there is no 2-dimensional load instruction, right? Ultimately, when we're allocating that memory, and this will connect back to our threads in just a minute here, when we are accessing memory and we've allocated our memory, we specify something as int a of 25 by 16, but what that really looks like in memory is something that's maybe closer to int a, we'll call this int a linear of 25 times 16. Right? That's what, and it's bytes, but that's ultimately what gets allocated for us, right? The multidimensionality of our data types are a programmer convenience feature. The compiler, memory allocator, all those things, linearizes all of that for us. And that's true for all these dimensions. You could have the 3-dimensional example for up to 9. It would do the same exact thing. If I specify 25 cross 16, what really ultimately gets allocated is that many number of ints, or that many ultimately number of bytes. And consequently, when I'm accessing memory of ij, what I'm really doing is what? It's C equals A linear of what? You got it. It is I times 16 plus j. If I have it backwards, it doesn't matter, so who cares? Part of that depends on how it gets laid out, actually, right? If it's a row by row or column by column. So either answer is correct. There can't be a wrong answer for this. In C, this is correct how it would get done, right? Where it's actually going to probably get laid out row by row by row. So it's A of 0, that row. A of 1, that row. A of 2, that row. So for every row, actually we're offsetting by 16 each time. And then we're adding the j offset there. If we wanted to write that a little bit more generically, we could say something like C is A linear of I times width plus j, something like that, right? Plus width times j. That gives us our serialized access here, which is why, even though our code is just doing memory lookups in the beginning here, and I got to go back to the beginning where this is happening, we're seeing additions and multiplications happening in our code, in our assembly code in CUDA, but in any assembly code that we're writing here as well. Because somewhere along the way, and it's not guaranteed to be a power of 2, so you can't just do shifts and stuff like that, somewhere along the way, for an arbitrary access into an n-dimensional array, you are required to do some multiplications and additions to linearize that address back out. This is, equivalent operations that we are doing here. The compiler ultimately is doing that linearization for you, even if you yourself are not doing that linearization in your code. If now instead, I don't want to go too far with this, if we had int b of 36, 25, 16, being squares is irrelevant. I don't know why I do it that way. So b linear would then be of size 36 times 25 times 16 we have to be a little bit careful because, we're referring to I, J, K, which are arbitrary, and that's not the same as X, Y, Z. But as long as we can keep track of what we're doing, that would be then equivalent to what in accessing B linear? It's a little tricky. But once you have that, this is the same answer to the thread layout question.
I times 25.
We got the good part, plus K. We got that part. So that part's done. Okay, I times what? You're right. I think you have it.
25, or, yeah, plus 16, or plus J 16.
I times 25 times 16.
Oh, you want the whole.
It'd be both, right? It'd be I times 25 times 16. Because for every offset of I, that's an offset into a whole block of J dimension times K dimension. And now let's start to use that terminology, right? Now it's times, again, we gotta be a little careful with how we do this here. What is X, what is Y, what is Z? But we could call it something like I times 25 would be like Y dim times X dim. Again, the only reason I'm hedging a little bit here is because X, Y, Z aren't correctly defined for this scenario here. It's width, height, and depth, but it's the same exact thing that we are doing here for the thread layout. So I times Y dim times X dim plus J times what? X dim plus K. And that's our layout of, and if I got that wrong, the big picture concept is still correct here. That's our layout of three-dimensional memory structure and what an individual IJK or .x, .y, .z access would look like. And now we would have, instead of IJK, if I were to do, the way I wrote this would be Z, Y, X here. That would be now, for every Z value, that's a whole X by Y grid. For every Y value, that's an offset in the X dimension, and plus then our X offset into that. And that's exactly then why our thread block and block in a grid layout looks effectively like that. The only reason then it starts to get a little bit nastier is now the equivalent CUDA version would be something like int, E of, we're going to run out of variables, right? K, L, M, N, right? Where it gets a little trickier because then LMN would be potentially block layouts, thread layouts inside a block, and then IJK would be block layouts inside a grid. So it's not just one big memory, it's two different kind of hierarchical layouts of our memory. But otherwise, that linearization approach of generating effectively a unique ID is the same as generating a unique index into a linear mapping of threads to a linear mapping of elements of a multi-dimensional array is the same as our linear mapping of threads into a block or blocks into a grid or a combination of threads into a block and blocks into a grid. Starting bottom up on this slide here, this is the kind of common pattern, that 2D mapping to 1D. And it's using the CUDA built-in variables, but if we have a block dimension in X, that was like our width, what we were calling it before, width times our offset plus our index into that. So for our 9D mapping down into 1D, you first have to work from the grid down to the individual block. What is my unique block ID? Well, that's a 3-dimension to 1-dimension mapping. It should look basically exactly like that. That is, from blocks in a grid, if that's 3-dimensional, it should be Z times our X by Y dimension plus Y times our X dimension plus X. That is my attempt to give you exactly the same as that example there, basically, right? We can do the same exact thing for what is my now thread ID inside a block. It should be, although again we have to make sure we're using the right built-ins for our block dimensions and our thread index inside our block dimension. It should be the same exact thing. Thread index in the Z, that's an entire X by Y block of threads off, plus our thread index in the Y, that's an entire width off, plus whatever our index is in the X dimension. That gives us our block ID, just a single number that's unique for every block in our grid. That gives me a thread ID, that's a number that's unique for every thread inside a given block. We then have to combine those, right? If we want truly 1D offset into the entire workload, that would be now, given my block ID, I'm this XYZ dimensions off, plus whatever my offset is within that thread. Your code will not necessarily have the same exact amount of dimensionality, but your, what I was calling thread bookkeeping code, usually at the very beginning, potentially also at the very end of your kernel, is going to look something like this in almost all the kernels, that you are writing. Figure out from my dimensionality of my thread layout, which one am I? Which one can I be? And this is kind of assuming that given this ID, we just need a singular ID, but you can get pretty far at that, because even in this matrix multiplication example here, which is relatively advanced, we're still starting with that singular ID, and then we're carving out a subset of the total work. So just because you have that many threads doesn't mean your data is of the same exact size. So perhaps given this final ID, you're going to do the next 1,000 elements in memory. It doesn't need to be the very next element in memory, but it's a way of at least partitioning, starting with a unique ID that's unique to every thread, whether thread in a block or thread overall in your entire grid. Here's my starting point where I know, okay, I'm thread number 473. Let me figure out what work is mine to do relatively independently of all the other threads that I have here. Yeah, sure.
Do you know if there's a reason that like a unique ID like that isn't just provided as one of the given variables?
Well, I think it is and it isn't. My guess would be what ultimately happens is there. So that's a totally valid question. Well, first off, you don't always necessarily want to do it this way, right? You don't necessarily want to have each block in a grid having different work. You don't necessarily want to partition it in this particular way. So that's not an all-size-fits-all solution for it. For the fact that these are either compile time constants for some of these and kind of runtime constants for the other, I think what likely happens is there's very little actual arithmetic happening live when you actually have this in your code. So you have this in your code, and then at some point in block and thread and warp launching time, this maybe gets executed once or maybe not at all. That's something that it can kind of figure out for itself, given these kind of built-in IDs for it. Because otherwise, though, the point is that this is a common pattern. It's not the only pattern. You can do all sorts of weird things and do different IDs depending on what you need them for. But something along these lines will almost always be needed in your CUDA kernels. And so it's a good question, though. This example is incrementing an array given a different kind of potential layout here, and it shows this kind of 2 to 1 dimensional layout here. So if this is code that's just going to increment an array based on some scalar value input B here, that would be the CPU implementation of the same. The GPU implementation would then be using a kernel, stripping out all the other stuff that's going on here. One way we can then, given a single dimensional data structure, one way we can do the work is to say each thread is responsible for one individual element of that data structure. You can kind of look at it from kernel to main launching code, kind of the top-down approach, although it's not required the kernel be before the launching code in your implementation and source. Or you can do it kind of bottom-up, and there's value in doing both ways. You can figure out what's going on by looking at the kernel first, or figure out what's going on by looking at the actual launching of that. While in theory, you can have all sorts of different kernel launches for the same kernel with different dimensions. In practice, there tends to be a roughly 1-to-1 relationship that you write the kernel's efficient when launched with a very particular kind of set of parameters and less efficient otherwise. In this case, what do we have? We have a block size, which is just a number of blocks. So that's a scalar, so that's just one dimensional there. You'll have a .x, block dimension .x is what that would be. Grid dimension .x is what that would be for that. Then you also have just a single dimension here for the total value n, so that each thread is responsible for just for one unit of work here. And you'd be launching a certain number of blocks in the grid and a certain number of threads then in each block. They would all just have the x dimension here. So for each thread, one way we can do this kind of linearization of our block and grid dimensions to a singular ID is just to say, well, which block am I? That's an offset of this many threads, because that's our grid layout there. That's our block dimension in the X. Then offsetting additionally, what is my own individual index in the X dimension here? That will then give thread 0, thread 1, thread 2, up through thread n at the end of the day. And this is, again, kind of a textbook example, but each then thread is responsible for just one unit of work that we have here. Let me shift gears because I want us just to use every possible minute we have here today. There's a couple more modules, but this is one that I can at least start on because we did touch upon it on Tuesday. This is this concept of branch or warp divergence, where I mentioned that this is an implementation-specific detail separate from kind of the big picture architecture, but that we limit of, all of our threads executing the kernel are doing the same instructions ultimately, but then we have this separate kind of individual schedulable piece of work referred to as a warp. That's each subsequent 32 threads in a block are connected together via this mechanism referred to as the warp, and that's the individual unit of schedulable work here. You're not scheduling individual threads, you're scheduling a warp of threads at a given time. That puts an extra restriction in terms of what is possible within the warp that isn't otherwise the case within the threads within a block. All those threads in the block are executing the same set of instructions, but all the threads inside a warp are executing the same instructions. They are executing in lockstep with each other. All the threads inside a warp then basically have the same exact program counter. There aren't 32 program counters for those 32 threads. We looked at it from the architectural diagram on Tuesday. There was just a single instruction fetch, because for a given warp, there is just a singular instruction that is closer to your vector SIMD type of style of execution for the warps, those 32 threads that comprise a warp. But what we started to talk about on Tuesday, and I just want to bring it up again and kind of expand upon it a bit today, is what happens when I have some actual control flow inside my kernel. And that's just going to be a natural thing that happens, right? That while there's hopefully large swaths of your kernel in which everybody is just doing the same computation and the different work is being figured out and partitioned via just a memory partitioning, but at some point you'll have some conversion. You'll have an if statement in your kernel. It's not something to necessarily be afraid of. But depending on why that's the case, you will have this mechanism for which different threads, even within that same warp, are potentially wanting to execute different parts of your code. For traditional threads, there's no issue whatsoever. They each have their own program counter, so it doesn't matter. Let this thread do this, let this other thread do that. Let this one take the true branch, let this other one take the false branch of your if statement. For threads within a warp, that becomes a problem. There's just a single program counter. How do we maintain this kind of lockstep execution here? And the answer, I think, leads to a kind of an implementation choice that's a little unique, and that's why I thought it'd be interesting to bring it up again here. The warps are then effectively serialized. Although, like with everything I've been talking about, there's caveats for what is possible in 2023 versus maybe what would have been possible 2 years ago. The right mental model is still to have that your warps are effectively serialized here. That if you do have, as this example is trying to show, a branch instruction with a subsequent branch instruction, and then the branches end at some point and they collect back at the end of all those branches, you have a serialization of that execution. Your code is not executing an if branch or an else branch. Your code is executing both effectively. That's what I mean by serialization. From an assembly perspective, we know that serialization happens, right? Branches are implemented via jumps to different labels in your code. You have the code for the if branch, and then you have the code for the else branch. It's serialized in terms of how the assembly is generated. Likewise, now what is unique here is that if it's threads within a single warp, we don't necessarily even take the branches that are there. We calculate whether or not the branch should be taken. And I mentioned this predicate instruction, and we'll talk about that again here. It is like a control code or like an ALU flag. You'll hear different terms referring to the same general concept. But here we use those control flows or those ALU flags to set a predicate to determine not whether or not we take left side or right side of our if statement here, or our branch instruction here, control flow graph here. But whether, when we do execute both sides of that branch, which side of that should actually correspond to an instruction that commits the result, that actually generates a change in our register file or reads or writes some value of memory at the end of the day. And so as these warps are being executed, we serialize the execution, and we're just effectively masking out the threads within the warp that should be active at any given point in time. But they're all executing, if this is instruction A through G here, they are all executing instructions A through G. And then back to A if we have a for loop here. But given some thread-dependent if conditions, if R1 is greater than 7, go left, otherwise go right. Certain threads at any given point in time will be active and actually executing that part of the branch. Other ones will be predicated out or masked out. And they'll still be doing the same instruction fetch through write back phases of the execution of it because they're all running entirely in lockstep. But ultimately, from an implementation perspective, it's probably something as simple as we're masking out the write enable port on the register file. We do all the work because everything is staying in lockstep. But if I'm this fourth thread here and I was not meant to take branch B, I was meant to take branch F instead for that initial A branch here. I do all the same work all my companion threads in the warp are doing here. I just don't write back the results. And when we finally do get to F as it's serialized here, this fourth thread here is just kind of not exactly wasting its time, but it's executing all the same instructions as if it was taking those branches, just not committing any of those results. Only after the fact is it then finally gets to take its F branch here. That is inherently different than taking a branch, right? If it was taking a branch, we would go from A to F, and we would deal with all the penalties associated with that, right? A big part of 381 when you talk about pipelining, when you take 581, you learn advanced kind of superscalar and other approaches, is that those branches are not free. They mess up our pipeline pretty good, right? Because we don't always know whether we should be taking the branch, and we may have to flush things from our pipeline when we wind up taking a branch here. The solution here is to not sweat it, to both take the branch and not take the branch, but then just keep track of, should I actually be executing those instructions on the other side of the branch? The downside, though, and I don't know if the example I have is really going to show that from like a final performance result, is that depending on how convoluted your branches are, you're going to have this issue of warp divergence. You can kind of see it here, but you can imagine all sorts of scenarios in which you have all sorts of different branching paths in your code. You have 32 threads in your warp, and if maybe only one of those threads is doing any work at any given time, yeah, you don't have branch hazards, control hazards, and things like that in this implementation, but you have a bunch of threads that are doing useless work, that are doing all the steps of the instruction but not actually committing any results. They're sitting in like the unshaded region here where they're not actually doing anything useful. In this case, single branch, not that big of a deal. Second branch, I guess it shows that a couple threads take the C branch and other threads take the D branch. This is meant to be instruction by instruction here. Not that big of a deal. In a more complicated example, you may be spending a lot of your time with threads inside your warp, not having any useful work to do. And you may have high occupancy, but you may not have good performance here. And here's just an example of how, without even really necessarily thinking about what may be happening, you have two pieces of code that may look very similar at first blush. I have this code that I can run. The results aren't that impressive. The compiler is doing something behind the scenes that is tricking me a little bit. But imagine these two versions of effectively the same kernel. We do our bookkeeping. Okay, I have my unique ID. That's what my unique index, right, that I've calculated. I've taken to heart that linearization approach, and I've applied it to this kernel in both instances of these kernels. This version of the code does a simple check on the ID, and depending on if my ID matches that condition, I call long function A, which is presumably doing a lot of work. Otherwise, it calls long function B, versus this version that is checking based on that index whether or not I'm in the first half of my block of threads or in my second half of block of threads. This version presumably is going to have fewer diverging warps than this example is going to have. Why do we think, based on this ID, why is this one going to be problematic? Not bad code. It's a valid way to split up work. I've cut them, in both cases, I've cut the work in roughly half. Half my threads do A, half my threads do B. Why is function 1 worse than function 2?
You assume the warps are like sequentially made, that every other thread is going to be doing a different branch.
That's exactly it, right? This approach, what is it doing? A bitwise AND with one. It's checking if it's odd or not, right? That's an odd detector, basically. If I'm an odd index, do A. If I'm an even index, do B. And while I think that's potentially subject to change, we generally can assume that's how our warps are getting formed. Give me the first 32 threads in my block. Give me the next 32 threads in my block, and so forth. Chunk them off 32 kind of sequentially. There'd probably be no reason to do it any other way, so I think that's a valid assumption to make. In this case, you will have kind of 50% divergence. In every warp, half the threads will be calling A, half the threads will be calling B. Here, we may still have some divergence because depending on how we cut the total thread block in half, it may not be a multiple of 32. There's no way to guarantee that that's necessarily the case here. But that would lead to maybe one diverging warp of all the warps that we have here versus potentially all the diverging warps. Now, the reason this may or may not be that bad, and when I actually run it here, and I can run it, I have it open. When I run it here, in this case, I may have to clean it here. Looks pretty similar. I may have commented something out because when I last checked it, it was a different result. Sometimes it's a little tricky that when you've run something else, it's kind of reusing results. So let's do matrix multiplication again, see if that changes our results. Well, isn't that lovely? Okay, so in this case, the results are exactly the same. It's probably clever enough to recognize that when you have this kind of scenario, this approach to masking warps, it can also do branch instructions. So if you know that there's a really long kind of path of divergence here, it should be intelligent enough as basically a compiler or even a runtime to determine, hey, I have a really long branch A and a really long branch B, just branch. And that part should be okay. Where you would likely have worse performance than that example showed is where you had maybe spaghetti code, where you had lots of small little if statements sprinkled throughout your kernel versus this example, which is one very long kind of if statement inside your kernel. Yeah.
So, like if all the threads in a warp take one side of the branch, does it do more of a traditional branch? Or
so you can still do traditional branches. So there is still a branch instruction here. We saw an example of it in our matrix multiplication, assembly code. It was at the very end of all that loops here. But let's talk about what that branch looks like in practice, because it is something that other architectures also do, but it may not be architectures that you are exposed to. So this is this approach to doing the masking, and this is referred to as predicated execution. Did any of you learn about this in 488? Did this come up at all? ARM doesn't really do it anymore, but this is also the case that ARM architectures used to also have predicated execution. As with everything, there's trade-offs. So one approach isn't better than the other. There's just different ways of trying to solve this fundamental control flow and pipelining kind of problem here. So the concept of predicated execution is that you don't really treat branch instructions as your only way of doing control flow, and that every instruction can optionally have control flow associated with it. So basically, every instruction can be so-called predicated, right? My decision is predicated on some other fact. So I'm waiting for some result to be true before I do something. Every instruction can then have that predicate associated with it. So every instruction can be essentially a branch. And similarly, the branch instruction, it's still called branch, but it's actually an unconditional branch. It's what you would think of as a jump instruction back when MIPS had a separate jump versus branch instruction. I'm always taking that branch. It's not branch less than, it's not branch greater than, it's just branch. So it's a jump instruction, right? But we can predicate all of our instructions, including that branch instruction, with some condition. It's the explicit kind of condition code or ALU flag or control code saying, if P1 is true, execute the instruction normally. If P1 is false, in some way, shape, or form, treat that instruction as a no-op. There, that's an implementation-specific detail. if I wanted you guys to implement it, I would probably just say, just as you generate the control signals for that implementation, just mask out the memory request, mask out the register file write. And for this kind of pipeline, that's probably good enough. You don't really necessarily have to treat it as a proper no-op. But that's what's happening here. We are executing all the instructions potentially instead of having explicit branches, and we're setting that code, setting that predicate, and then we're allowing for all these instructions to kind of be treated as a one-line branch instruction, right? As an instruction that either executes or doesn't execute. This kind of version for very small branches is still what happens, in these modern GPU architectures. If in my C code I had something like if x is equal to 10, set c equals c plus 1. So a one-line if statement here. You should probably still put brackets, it's good programming because it's one-line if statement today, it might be a two-line if statement tomorrow, but fine. One-line if statement does not require our brackets. If it's equal to 10, add 1 to c. We grab our value of x. We're doing some sort of equality test. So the actual instruction is called set predicate. I think there's an example of it on this slide. Set predicate for less than equal to, comparing the two values as signed 32-bit integer values. If, in this case, register 39 is less than or equal to register 2, set predicate value just called P2. So this is more of a pseudocode here, but it's doing the same exact thing. If R5 is equal to 10, set predicate P1. And then for the what gets compiled as inside the if statement here is going to be executed by every thread. For some threads, perhaps x is equal to 10. For other threads, perhaps x is not equal to 10. But even if you just think of a single thread, and with an ARM architecture executing a single thread, it's the same concept. We set our predicate. We don't do branch equal. We still could, but we don't have to do branch equal. We instead, for every one of those instructions that would be inside the if statement, we predicate them. We say, do a load, an add, and a store to get C++, C equals C plus 1 here, and predicate all three of those instructions based on that condition of P1 here. It's an alternative to branching. Your pipeline's happier, right? And in this case, our warp execution is happier, because no matter what, we execute all 5 of these instructions. Just that sometimes 3 of the 5 are kind of sort of wasting their time, right? They're doing work that's not going to get committed anywhere. And then for other parts of the time, all 5 instructions are doing something valid. That is a design trade-off, whether I want to do this or whether I want to have a branch instruction is a design trade-off that's either made architecturally or made at compile time or some other runtime implementation decision to make, whether it makes sense to predicate a set of instructions or whether it makes sense to branch away from a series of instructions that you don't want to execute. Specifically now in the GPU compute in the CUDA context, because of this limitation of how we are scheduling threads in a warp that allows us just to have a single program counter and a single instruction fetch kind of field to memory, predication for very small branches can be a performance improvement. Even though the warps are diverging and some are doing left and some are doing right and we're executing all the instructions, it may still be beneficial to do that versus just doing a branch instruction. Now, this kind of information is something that is occasionally documented and other times not documented. These instructions still exist. So you have these predication instructions that say set a predicate, set a value that's a true false value, and we'll use that for subsequent instructions here. But when we decide, as you write C code, to generate predicates versus generate branch instructions, really depends on the underlying architecture, compiler options. You might be able to tweak it as well. Whether or not you actually implement it as a branch or whether or not you implement it as a set of predicated instructions here. But I would have liked to show a difference in performance. We'll leave things there. That's kind of appropriate for the demos we've had all semester. They kind of sort of work. I'll have to check. Sometimes I comment things out and forget to change what I commented outside to recompile. Let's leave things here for today. There's other reasons that cause less performance, and you can look ahead and look at memory coalescing and things like that. That's kind of equally important here, but we're just going to run out of time to get to it. Between now and Tuesday, your life should be your projects, and you'll be just fine on Tuesday. But let's have fun with it, okay? I mean, this is kind of an end of semester celebration. You have all succeeded. You should all feel good about what you've learned and how far you've come from the start of the semester. So let's celebrate on Tuesday. I'm just excited to see the demos, and let's have some fun with it, okay? Otherwise, that's it for the semester. Please fill out the course surveys if you have not yet. Otherwise, when only one of you fills it out and that person's unhappy, I get one disgruntled result, and that's just not good for me. So I prefer if everyone does it, and if all of you are disgruntled, so be it. I mean, I'll just live with that result. But I'd like to get a statistically valid sampling of the very small class we have here this semester. So if you have not done that, please do so, and I'd really appreciate that. Otherwise, enjoy the rest of your semester. I'll see everyone on Tuesday.